All right, calculus friends, integration by substitution. This will be example 2, part A. So one thing that you'll notice from the screen to the board here is I've done the rewrite that we've been talking about a lot. It is often beneficial to use negative exponents or, in the case of radicals, fractional exponents. So you'll notice that we rewrote this as that quantity to the negative third power and brought it upstairs. There is not a quotient rule for integration, so this is something we would need to do to get the ball rolling. Another thing that's different now about this question is you notice this time we have limits of integration, and therefore this would be an example of a definite integral. So that would be Roman numeral 2 in your notes, definite integrals. We don't have to pause to write the notes, so we can buzz through this quickly, and again, you can always hit pause anytime you want. But again, we will usually substitute. If we have a quantity to a power, that would typically be what we want to replace with the single variable u. So much like we practiced on example 1, we'll jump over here and we'll change that quantity x plus 1, which is being raised to a power. We'll replace that with the single variable u. And so at this juncture, the new integral over here will now be u to the negative third power, all right, set a quantity to a power. So we've talked about that before. We will usually substitute if we have a quantity being raised to a power. Also, remember that we always want to replace the dx. So just like all of the previous examples, example 1, watch them in sequence, it helps. We differentiate both sides with respect to x in order to create a dx. So this would be du dx, and this would be just simply a 1, wouldn't it? Clear fractions. And so it turns out that in this particular example, du is exactly equal to just straight up dx. And so therefore du can take the place of the dx in the original. So far this is identical to examples 1. All those 6 examples we did earlier, we want to make sure we replace every single expression in the original integral. And thus far we have. So far it's identical to what we saw on example 1. We want to make sure to substitute for every single expression in the original integral. And we've done that. But this has limits of integration. This is a definite integral. Not only do we replace all of these expressions within the integrand, but we also want to remember to substitute the limits of integration. All right? And so the way we do that is we look at this and we say, well, you know what? That 1 there is a value of x. Remember, these are on the x-axis. We're integrating from 1 to 2 on the x-axis. These are values of x. And just like every other thing, we change those x's into u's with that original substitution. So the idea here would be that we will take this 1 here and put it in there for x. It's a value of x. 1 plus 1 is 2, so that lower limit of integration in the original integral, when you put 1 in for x, 1 plus 1 is 2. So when x is 1, u would equal 2. So you notice this changes over here to a 2. So we're substituting everything, and everything gets replaced off of that original integral right there. All right, and then let's see, I haven't used a box yet, I guess. That upper limit of integration, that 2, is also a value of x. So if we put 2 into our original substitution here, for x, 2 plus 1, u would equal 3. This is the step that is very easy to forget to do to change those limits of integration. So notice that's capitalized and underlined. Make sure you change your limits of integration. Now the beauty of this is that if we change everything, including the limits of integration, we can complete the question over here and never go back to our x, all right? So unlike an indefinite integral, on this one, we're done. We leave our x, never go back, and we simply finish the question from here. So from here on, since it's now a definite integral, we're back to the integrate, evaluate, and celebrate. All right? So, the integral from 2 to 3, let me clean it up a little bit, u to the negative third dx would equal, we find the antiderivative, which would be what? U to the negative 2 over negative 2. Remember, that's that step where we find the antiderivative of that function, n plus 1 over n plus 1. Then we show that we're about to evaluate here. So then we change that integral over to that symbol we use, you recall, when we want to evaluate. I would suggest in this example that we go ahead and rewrite this expression first. So that would be the case. I'm kind of running out of room, but I'm going to take that u to the negative 2 back underneath. So this expression would simplify to negative 1 over 2u squared. Take that underneath. I move the negative upstairs. A couple little algebra kind of things here. And so that was a little bit of a rewrite of that expression. And then the evaluate step, right, which again is to plug the numbers in. So in this example, we would put the 3 in for u. All right, and so that would be the f of b minus f of a discussion that we've had many times here. And so that would be negative 1 over 2 times 3 squared. And that would be that upper limit of integration plugged into that antiderivative. Minus, remember the f of b minus f of a discussion that we've had on previous episodes here. And then you put the 2 in there. So this is just mechanical arithmetic at this point. And then that one would be negative 1 over 2 times 2 squared. All right, so that's again the f of b minus f of a. And then it's arithmetic after that. And this particular one evaluates to 5 over 72. And you'll notice a major difference here is we do not go back to the original integral. We do not substitute back. If we change everything, it's like we're leaving our x and we're replacing everything and we're running off with u and we're definite about things. We're never going back. So if you change everything, including your limits of integration, finish the question. And there's your answer in this example, 5 over 72. So let's practice a few more of those, shall we?